this lecture we continue our discussion on heuristics to solve the travelling salesman problem. In the previous lecture we were looking at the heuristic based on matching. We start with the minimum spanning tree for the data that is given in the problem. We consider the same data here, and the minimum spanning tree which we have already drawn is like this. So, the minimum spanning tree has these 4 edges, 2 to 4, 2 to 5, 3 to 4 and 1 to 5 with length equal to 26, 8 plus 5 13 plus 6 19 plus 7 26. We also mentioned in the previous lecture that in the minimum spanning tree the number of vertices that have odd degree will be even. Now, this is a vertex that has odd degree. These 3 vertices have even degree equal to 2. There are 2 edges here. This is a vertex that has odd degree equal to 1. So, the number of vertices with odd degree will have to be even. We even mentioned in the previous lecture that this is an important result. It is a very easy result to prove, because each edge is incident to 2 vertices, and therefore, the sum of the degrees of every vertex when added is an even number, because each edge contributes to the degree of 2 vertices. So, sum of the degrees of the vertices is an even number, and because the sum of the degrees of the vertices is an even number, the number of vertices that have odd degree is even. So, in this case there are 2 vertices that have odd degree. We could have a case where 4 vertices have odd degree, because we are considering a 5 by 5 problem. So, if we have only 2 vertices that have odd degree, all that we do is go back to that matrix and add that vertex. For example, 1 and 3 are the vertices that have odd degree. So, add the edge 1 3 into the minimum spanning tree to get a Hamiltonian circuit, or to get a feasible solution to the travelling salesman problem. If we do that, now 1 3 has weight equal to 8. So, there is only one feasible solution here, which is a feasible Tor, feasible to the travelling salesman problem. So, this will have a length equal to 34. So, this method for this particular problem gives a feasible solution with length equal to 34. If the number of vertices that have odd degree is 2, then we add only one edge into the minimum spanning tree to complete it, and therefore, we have only one solution that is given to this problem. Now, for this instance, that solution gives a length equal to 34. Now, we may have the case where there are more than 2 vertices, an even number, it could be 4 vertices that have odd degree, or for a larger sized problem we could have 6 vertices or 8 vertices that have odd degree. So, let us see what happens in such a case. Now, let us assume for a moment that the minimum spanning tree is like this. In our example it is not so, but let us assume for a moment the minimum spanning tree is like this. Now, this is a case where there are 4 vertices that have an odd degree. So, when there are 4 vertices that have an odd degree, what we do is we go back to the original matrix and then pull out the corresponding 4 by 4 from the original matrix. The original matrix has vertices 1, 2, 3, 4 and 5 with 1, 2, 3, 4 and 5, and we pull out the corresponding 4 by 4 matrix. If this were the minimum spanning tree, then the 4 vertices that we are interested are 2, 3, 4 and 5 that have odd degree. So, we pull out a corresponding 4 by 4 matrix out of this. What we do is we try to find out what is called the minimum weighted matching. Now, this is always this number is always an even number. It's either 4 or 6 or whatever, depending on the size of the matrix. Now, in this case it is a 4 by 4. Now, when we have a 4 by 4 matrix, what I mean by a matching is this. Now let us look at the edge 2 3 and the edge 4 5. Now there are 4 vertices. So what we try to do is with 2 edges such that these 2 edges do not share a common vertex, we try to exhaustively look at all the vertices. A typical example of a matching could be 2 3 and 4 5. Now there are 2 edges, there are 4 vertices divided by 2 edges, and all the vertices are covered. Another matching could be 2 4 3 5, and a third matching could be 2 5 3 4. At this case there are only 3 possibilities. If it were a 6 by 6, then we will have more possibilities. Every matching will have 3 edges that will cover all the 6 vertices. Now here we have 3 possibilities. Now we find out the weight associated with each of them. The weight associated with this is 2 3 plus 4 5, which is 10 plus 6, which is 16. The weight associated with this is 2 4 and 3 5, which is 8 plus 6, 14. The weight associated with this is 2 5 and 3 4, which is again 8 plus 6, which is 14. Now out of these 3 we find out the best one, which can be either this 14 or the other 14. So let us say we take this 14 and then we superimpose this matching onto the minimum spanning tree. So we would get something like this 2 to 4 and 3 to 5 on this. Now once we superimpose this matching onto the minimum spanning tree, we can try and get an Eulerian circuit, which means starting from any vertex we will be able to go to every edge once and only once and come back to the starting vertex. Now such an Eulerian will look like this. For this example it will look like 1 to 2, 2 to 4, 4 to 1, 1 to 3, 3 to 5 and 5 to 1. So we will have an Eulerian circuit like this, and as we did in the earlier case, we can go back and get feasible solutions to the travelling salesman problem. They could be 1, 2, 4, 3, 5, 1, 1 to 2, 2 to 4, 4 to 3, 3 to 5, 5 to 1, or it could be 1, 3, 5, 2, 4, 1, 1 to 3, 3 to 5, 1 to 3, 3 to 5, come back, 5 to 2, 2 to 4, 4 to 1, or it could be 1, 4, 3, 5, 2, 1. We can do no. So we have only 2 cases, 1 to 4, 1 to 2, 2 to 4, 4 to 3, 3 to 5, 5 to 1, and we have the case starting with this one, 1 to 3, 3 to 5, 5 to 2, 2 to 4, 4 to 1. So these are the possibilities that we have, and we can find out the LH associated with each one of them and choose the best. So when we had in our spanning tree only 2 vertices that have odd degree, we simply add that edge and proceed. When we have more than 2 vertices that have odd degree, then we pull out the corresponding matrix from this matrix, and then we find out what is called the minimum weighted matching, superimpose the minimum weighted matching onto the spanning tree, obtain an Eulerian circuit from which obtain feasible solutions to the travelling salesman problem, and then find out the best out of these and declare them or give them as the heuristic solution to the problem. Now how good is this algorithm? Now can we derive an expression like what we derived for the twice around the tree heuristic? It is possible to do to have a derivation for this, which we will look at right now. Now let us try and derive that expression for this here. Now let us call the best out of these as LH, and if triangle inequality holds, like we discussed in the earlier case, if triangle inequality holds, we can show that, for example, this has been brought out of this. This is 1 2 2 4 4 3 3 5 5 1. So, if triangle inequality holds, 4 1 plus 1 3 is greater than or equal to 4 3, therefore, this length is greater than or equal to this length. If we call this length as LE, length of the Eulerian, then LE is greater than or equal to every one of these LH, and therefore, LE is greater than or equal to the best out of these, which we are going to call as LH. So, we have this simple relation, LH is less than or equal to LE, which we can show if triangle inequality holds, where LH is the best among these that we have taken. So, we write the first result, that LH is less than or equal to LE. Now, what is this LE? Now, this LE is nothing but the length of the minimum spanning tree plus the length of the matching that we have added on to this. So, LH is less than or equal to LE. Now, we have LE is equal to LMST, length of the minimum spanning tree, plus length of the matching that we have added to the minimum spanning tree. Therefore, LH is less than or equal to LMST plus L matching. We already know that LMST is less than or equal to L naught. So, LH is less than or equal to L naught plus L matching. Now, we have already written LMST with reference to L0. Now, we need to write this L matching with reference to L0, so that we will be able to derive LH by L0. Now, what is the relationship between this L matching and L0? Now, let us go back to this. Now, let us look at the case where we have 4 vertices having odd degree. Now, let us say that we have some unknown L naught. For this problem, there is an unknown L naught which has 5 edges here. Now, we do not know exactly what is L naught, but one thing that we know is that all the 5 vertices are actually present in L naught. So, for the moment, let us assume that the L naught, since we know the L naught, so let us assume that L naught is 1, 3, 4, 2, 5. We can actually derive this by assuming that we do not know L naught. Just to make the derivation simpler, I am assuming that we know the L naught, and I am going to show this to you. Now, this is 2, 3, 4, 5 that are here. So, what I do is I simply take 2, 3, 4, 5. So, what I am trying to say is that it is always possible from L naught to remove edges and bring it such that we have a smaller thing corresponding to these vertices that we have here. Now, again, based on triangle inequality, this plus this is greater than this. Therefore, the L34 plus 42 plus 25 plus 35 is now less than or equal to L naught. Now, we have this. Now, for these 4 vertices that we have the matrix here, and we have found out what is called the minimum weighted matching associated with this, which means we have looked at 2, 3, 4, 5, which is not here. Now, if we take a matching out of this, if we take a matching out of these 4, there are only 2 possibilities. 3, 5 plus 2, 4 is one matching, 3, 4, 5, 2 is another matching. If we take a matching out of this, we say 3, 5, 2, 4 is one matching, and 3, 4, 5, 2 is another matching. Now, the minimum of these 2 will have to be less than or equal to half of this. Now, let us call this length as L 2, 3, 4, 5 L2, let's call this as L2534 as this length. By triangle inequality, L2534 is less than or equal to L0 because 1 3 plus 1 5 is greater than or equal to 3 5. So, L2534 is less than or equal to L0. Now, from this 2534 we may get two matchings which are either 3524 or it can be 3452. Now, the minimum of these two will have to be less than or equal to, now let us call this as some L small m, small matching. Now, this Lm which is the minimum of these two should be less than or equal to L2534 by 2. This is like saying if we add if we add these 4 lengths, for example 2 5 is 6, this is 6, 2 4 is 5, 3 4 is 8 and 3 5 is 9. Now, we can look at two matchings. The total is 9 plus 8 17 plus 5 22 plus 6 28. One matching is 14 3 5 and 2 4. So, this is 9 plus 5 14, the other is 8 plus 6 14. Now, you see that this is the minimum of them has to be less than or equal to 28 by 2. It is just like saying I have a number, I divide it into two numbers, and if I divide it into two numbers such that the sum of these two is the given number, the minimum of the two should be less than or equal to half of it. So, it is a very simple result from which we can say that this Lm is less than or equal to L2534 by 2. Therefore, this Lm is less than or equal to L0 by 2. Now these are matchings that are got from this, and what are these? These are matchings that are got from the complete graph associated with this. Now, the complete graph is here. Now, these matchings are also part of this. For example, 3524 is here and 3452 is also here. So, when this is part of this, when we identified this, we looked at 3 4 5 2 and we looked at the complete graph which was the 4 by 4, and we identified the minimum matching out of this complete graph. Now, this is part of the complete graph, and then we identified the minimum matching associated with this part. So, the minimum matching that we get from here will again have to be less than or equal to the minimum matching that we get from here. Therefore, the L matching is less than or equal to L0 by 2. Now, this is less than or equal to L0 by 2. Now, L matching is less than or equal to Lm. Therefore, L matching is less than or equal to L0 by 2. So, this will be less than or equal to L0 plus L0 by 2. So, this is less than or equal to 3 by 2 L0. So, LH by L0 is less than or equal to 3 by 2 or 1.5. Now, again just to explain again this L0 by 2, let me quickly do that one more time. This is the little more involved portion. Up to this it is fine. What we try to do is the following. Now, if there is an unknown L0, the moment we know that these are the vertices, it is always possible to do something like this. That is, in this example, just to leave out one will have to be connected to either 2 out of these 2, 4, 3 and 5. It is like just leaving one out of the L0 and joining the rest of them to get this figure L2534. This L2534 is derived from L0, assuming that L0 is not known, but the only thing we know is that no matter what is the optimal solution, this L2534 will be less than or equal to L0 based on triangle inequality. So, because this one has been left out, so L2534, which are corresponding to the vertices that have odd degree. Now, that L2534 will be less than or equal to L naught. Then we go back and say that it is always possible to get a matching out of this, and the minimum such matching will be less than or equal to L naught by 2. So, Lm is less than or equal to L naught by 2. Then we go back and explain that this is only a part of the complete graph from which we have got a minimum matching. This is the complete graph from which we get a minimum matching. So, obviously, the one that we get from the complete graph, that minimum matching should be less than or equal to the matching that every matching that is obtained out of this. So, the L matching will be less than or equal to this Lm, which in turn is less than or equal to L naught by 2, and therefore, L matching is less than or equal to L naught by 2. So, LH is less than or equal to L naught plus L naught by 2, which would give LH is equal to 3 by 2 L naught. So, whenever we have n is odd, if we have n is equal to 5, then the number of vertices that we may have to look at is either 2 or 4. So, for 4 we went back and did this. Now, for 2 what do we do? Now, in the case in the actual case where 1 3 were the only 2 vertices that had an odd degree, and the spanning tree actually looked like this. So, the spanning tree had 5, 2 to 4 is 5, then 2 to 5 is 6, 2 to 4 is 5, 2 to 5 is 6, 5 to 1 is 7, 3 to 4 is 8, when the spanning tree look like this. And then we actually do not know L naught, but if we assume that somewhere only 1 and 3, so what we do is we do not know, but let us assume that 1 and 3 are here and we simply put this. So, by triangle inequality, this 1 3 L 1 3 is less than or equal to L naught, because L 1 3 is less than or equal to this plus this. Therefore, L 1 3 is less than or equal to L naught. So, simply adding 1 3, again we are adding a quantity that is less than or equal to L naught by 2. We can even prove that actually L 1 3 is less than or equal to L naught by 2, because from triangle inequality this portion L 1 3 is less than or equal to sum of these two, and L 1 3 is less than or equal to sum of this plus this plus this. Therefore, L 1 3 is less than or equal to L naught by 2. So, even when we are adding only one edge into this, we are adding an edge whose weight is less than or equal to L naught by 2. So, whenever the number of vertices with odd degree happens to be less than or equal to the actual number of vertices, we assume that we actually use triangle inequality to get this and prove that whatever is added into the minimum spanning tree has a weight which is less than or equal to L naught by 2, and therefore, LH by L naught is always less than or equal to 3 by 2. So, this heuristic based on matching, based on minimum matching, now has a worst case performance of 3 by 2, which means no matter what the size of the problem is, no matter what these numbers are, as long as the data satisfies triangle inequality, we can get a heuristic solution which is at most 50% away from the optimum. So, these kind of heuristics also give us an opportunity to understand how to derive or evaluate the worst case performance of these heuristics. It is possible to do this for certain heuristics, it is not possible to do for certain others, and those heuristics for which we could get this kind of an analysis, they are called approximate algorithms. Once we define a heuristic as an approximate algorithm, then it means that there is an expression or a derivation for the worst case performance of the algorithm. Now, we move on to look at some improvement heuristics for the TSP. So, we look at some improvement heuristics. Look at some improvement heuristics. Now, improvement heuristics means you already have a solution and you are trying to improve it. In a construction heuristic, you do not have a solution, you build or construct a solution. Now, all the 3 or 4 heuristics that we saw, the nearest neighbor, the one that was based on the branch and bound, the twice around the tree heuristic and the heuristic based on the matching, they are all examples of construction heuristics. Now, let us look at some improvement heuristics. In order to get an improvement heuristic, you need a starting solution which we actually try and improve. So, let us look at a starting solution. Let us look at a solution 1, 4, 3, 2, 5, 1. Now, let us look at this solution. Now, this solution has length 1 to 4 is 9, 4 to 3 is 8, 17, 3 to 2 is 10, 27, 2 to 5 is 6, 33 and 5 to 1 is 7, 40. So, with LH is equal to 40. So, this has length equal to 40. Now, can we improve this further? A very simple thing to do is called pairwise interchange, which we can do. One of the easiest ways of doing pairwise is you take, incidentally we can the pairwise can be done in more than one way. Now, in TSP we generally leave this and we assume that we come back to this. So, the first thing we do is called an adjacent pairwise interchange. So, when we do an adjacent pairwise, I first swap just these two. So, I get 1 4 3 2 5 1. So, I do an adjacent I do an adjacent pairwise. So, I swap these two, I get 4 1 3 2 5, which means I will come back to 4. Now, this will give me a length 4 to 1 is 9, 1 to 3 is 8 17, 3 to 2 is 10 27, 2 to 5 is 5 32 plus 5 to 4 which is 6. So, this gives L equal to 38. I can do another adjacent pair with this. So, I try 1 3 4 2 5 and 1. So, 1 3 is 8, 3 4 is 8 16, 4 2 is 5 21, 2 5 is 6 27, 5 1 is 7, L equal to 34. We can try this adjacent pairwise to get 1 4 2 3 5 and 1. So, 1 4 is 9, 4 2 is 9 plus 5 14, 2 3 is 10 14 plus 10 24, 3 5 is 9 33, 5 1 is 7, which is L equal to 40. We can try this pairwise. So, we get 1 4 3 5 2 1 with L equal to 1 4 is 9, 4 3 is 8 17, 3 5 is 9 26, 5 2 is 6 32, 2 1 is 10 42. So, we can do these pairwise exchanges. There are 5 numbers. So, we can do 4 pairwise exchanges. If there are n numbers, we can always do n minus 1 adjacent pairwise exchanges. Each of these are called adjacent pairwise exchanges. So, we can do n minus 1 adjacent pairwise exchanges and take the best solution. In this case, the best solution happens to be 34. Now, at the moment we do not know that it is optimal. So, the next thing that we can do is to go back to this and then look at some adjacent pairwise exchanges that are possible, and then if there is no improvement, then stop the algorithm. That is one way of doing this. Another way, which is a slightly greedy way, is The moment we start with this 40 and the moment we get this 38, we then look at this 38 and continue to do pairwise exchange. That is also possible, but ordinarily you do one pass of the adjacent pairwise exchange and then leave it here, because even if we try and make pairwise exchanges out of this, we would still get some solutions, some changes, because this would give us the first exchange would give us 3 1 4 2 5 3 3 1 4 2 5 3. We have not evaluated this. So there is still a possibility that some changes can happen. So we can do one more pass of this algorithm to see if we can get an improvement. Of course, for this instant we won't get an improvement because we already know that 34 is the optimum, but then once we don't know the optimum, we can continue doing this till there is no improvement and then stop with the best solution that we have. So this is the adjacent pairwise exchange heuristic, which is an improvement heuristic. The next one is a general pairwise exchange heuristic, which means we can take out of these 5 and exchange all possible pairs. Now there are 5 nodes or there are 5 cities. So a pairwise interchange can be done in 5C2 ways, which is 10 ways. Let me just write down only those 10, and the first one would be 1, the given one is 1 4 2 3 5 1. So the first pairwise can be 4 1 2 3 5 4. The second one can be 1 and 3. So I will have 2 1 2 4 1 3 5 2. Then this exchange 3 4 2 1 5 3, and then this exchange 5 4 2 3 1 5. These are the 4 possible exchanges with 1. Then we look at this. Now this is 1 2 4 3 5 1, that is I am exchanging this 4 and 2. Now I exchange this 4 and 3, I will get 1 3 2 4 5 1. Then I exchange 4 and 5 to get 1 5 2 3 4 1. Now I have exhausted this. I come to 2 and 3. So 1 4 3 2 5 1. Then I do 2 and 5. 1 4 5 3 2 1. I have exhausted this. Then I come to this. I do 1 4 2 5 3 1. So I start with this and I have 1 2 3 4 5 6 7 8 9 10 possible pairwise exchanges. So this is NC2 number of exchanges, this is n minus 1 exchanges, and so on. You will also realize that this is a subset of this 10. So we can evaluate all these 10 solutions and then choose the best. That is a normal pairwise exchange heuristic or a pairwise exchange algorithm applied to the travelling salesman problem. Once again, in this instance we will get L equal to 34, because in the subset that we have evaluated we have already got the solution with L equal to 34. So we could do either an adjacent pairwise exchange, which means we evaluate n minus 1 new solutions in one pass, and then we do one pass of the total pairwise and then take the best out of this. Now we will have a small change in this and then we can do one more pass and proceed, because we can take the best out of this and then again do one more pass of NC2 and see if there is a further improvement. There will be some new solutions that will come in, while majority of the solutions will repeat, because here we have evaluated NC2 out of the possible n minus 1 factorial. N minus 1 factorial 24 solutions are possible. In this pass we are evaluating only 10 out of the 24 solutions. So once we get the best out of this, we can again subject it to another pairwise interchange, which means we will evaluate 10 more solutions and keep doing it till there is no improvement. So, we can either use an adjacent pairwise exchange or a complete or total pairwise exchange, where we evaluate n minus 1 solutions in one pass or NC2 solutions in one pass, and so on. Now, we look at another type of improvement heuristic, which is very specific to the travelling salesman problem. Now, that is called the 3-off heuristic. It is called the 3-off heuristic or a 3-way exchange heuristic. Now, if we look at a travelling salesman problem, let us assume we look at a travelling salesman problem. Let us say we have right now we consider a 6 city TSP, and let us call them these 6 nodes as A, B, P, Q and U, V. Now, what we can do is, for these 6 nodes or 3 pairs of nodes, it is possible to create some more feasible solutions. For example, this is one feasible solution. We could create AB, PU, QV. So, what does that mean? AB, PU and QV, which means A, B, P, U, Q, V, which means these two edges are they go and they are replaced by these two edges. Now, what we can do is, if we take three edges A, B, P, Q and U, V, then we can show that 7 new solutions can be obtained, including the given one. There are 8 solutions, but 7 new solutions can be obtained, one of which is A, B, P, U, Q, V. The others are A, P, B, U, Q, V, A, P, B, Q, U, V, A, Q, U, B, P, V, A, Q, U, P, D, V, A, U, Q, B, P, V and A, U, Q, P, B, V. Now, these are 7 new solutions that are possible. We also realize what is common in these, including the given one, is that the first one is always A and the last one is always V. The rest of them are shuffled inside. So, since there are 3 edges, you can do that in 2 to the power 3 ways. So, 2 to the power 3 minus 1 would give us 7 new solutions, one of which we showed as A, B, P, U, Q, V will now become A, B, P, U, Q, V. Let us try and show this A, Q, U, P and B, V. So, we show A, Q, now the new solution will become A, Q, U, P, B, V, which means it comes here A, Q, Q, P, P, U, this goes and this goes. So, which means this is not there, this is there A, Q, Q, P, this one is there, which means comes here A, Q, Q, P, P, U, U, V. So, this one is there, this one is there, this one is there. So, this one is left out, this is not there, this is not there and this is not there. So, 3 edges are replaced by 3 other edges. So, we have 7 such possibilities. Now, if the given problem has more than 6 nodes, which means it will have more than A, B, P, Q, U, V. For example, if we look at a 10 city problem, in a 10 city problem the AB, PQ, UV by itself can be chosen in 10C3 ways, or in general it can be chosen in NC3 ways. Now, if we have a 5 city problem like what we have, now again these AB, PQ, UV can be chosen in 5C3 ways, which are 10 ways, except that there will be repetitions as we move along. For example, if we choose in our, let us start with this feasible solution with length equal to 40. If we choose AB as 1,4, PQ as 3,2 and UV as 2,5, if we do that, then the first one will be AB, PQ, UV, AB, PU, AB is 1,4, so we include 1,4 AB, PU is 3,2, we are looking at this. So, AB is 1,4, PU is 3,2, QV is 2,5, which means we go back to this, we do 1,4, then we do 4,3, 3,2, 2,5, 1, which is the same as the given one. There is a repetition here. Whereas, if we look at this one, when we look at this one, we get AQ is 1, 2, UB is 2, 1, so which we cannot have, AQ, UP is 2, 3 and BV is 4, 5. So, AQ, UP, BV, AQ is 1, 2, UP is 2, 3 and BV is AQ, UP and BV is 4, 5. So, now what do we have? We start with 1, 2. So, what it means is we have 1, 4, 3, 2, 5, 1, 4, 3, 2, 5. Now, AB, PQ, AB is 1, 4, PQ is 2, 3 and UV is 2, 5. These are the 3. Now, we go to 1, 2, we go to 1, 2, then we use 2, 3, we again use 2, 3 and we use 4, 5. So, the new solution will be 1, 2, 2, 3, 3, 4, 4, 5 and 5, 1. This remains in the solution, this remains in the solution. So, we have 1, 2, 2, 3, 3, 4, 4, 5, 5, 1. So, this goes out of the solution, 2, 5 goes out of the solution. So, we get a different solution out of this. So, if we take AB, PQ, UV to be 1, 4, 3, 2, 2, 5 and then we can substitute in these. For example, this substitution would give us a solution with 1 to 2 is 10, 2 to 3 is 10, 20, 3 to 4 is 8, 28, 4 to 5 is 6, 34 plus 7, 41. This would give us the same solution with 40. If we look at this, for example, AP, BQ, UV would give us AP is 1, 3, BQ is 4, 2, UV is 2, 5. So, if we look at this, then our original solution is 1 4 3 2 5. So, we are adding 1 3. So, let me put it this way, we are adding 1 3, we are adding 4 2 and we have 2 5. So, I have the new solution is now 1 3 which I have added, 2 4 1 3 4 2 5 1, 1 3 4 2 5 1, because I have added 1 3 3 4 4 2, I have added 2 5 again and 5 1, 1 3 4 2 5 1 with L equal to 34. So, this would give us L equal to 34. So, like this for every AB, PQ, UV we can get 7 solutions, but if AB, PQ and UV are not distinct, as in our example there are only 5 nodes, therefore, we cannot get distinct AB, PQ, UV. So, when we do not have distinct AB, PQ, UV, you will not get 7 distinct solutions. You may have 1 or 2 solutions repeating as it happened here. The original solution came back again when we computed this. Nevertheless, for every AB, PQ, UV which can be done in NC 3 ways, we can get a maximum of, or we evaluate NC 3 into 7, some of which may repeat. It still does not matter. So, one pass of the 3-opt will actually do NC 3 into 7 solutions, some of which may repeat, and we may take the best out of the NC 3 into 7 solutions. For our example, we have already got this 34, and since we know that this is the optimum, we cannot have any more improvement over the 34. So, one pass will evaluate a maximum of NC 3 into 7, and then we can continue the passes till it does not show any improvement, and then the algorithm will terminate with the best available solution. In our case, it will terminate with this solution with z equal to 34. So, the improvement heuristics, we have seen 3 of them. One is the adjacent pairwise exchange heuristic, the other is the 2-opt or the pairwise exchange, and the other is called 3-opt. Now, 3-opt is a very famous heuristic. This came in the year 1971 and is proposed by Kernighan and Lin. It is a very famous heuristic even today for solving the TSP, particularly large instances of the travelling salesman problem. But all the improvement heuristics essentially work on the idea that we have a solution and then we try to improve the solution using these heuristics. So far in the travelling salesman problem, we defined the TSP and we saw the formulations, and then we saw some branch and bound algorithms, 3 types of branch and bound algorithms to solve. Then we saw some heuristics, some number of construction heuristics and some number of improvement heuristics. Now, we look at one more aspect of the travelling salesman problem, which we again use the same matrix and help and study this aspect of it. Now, usually in the travelling salesman problem, we said the person starts in any city, goes to every city once and only once and comes back to the starting point. Now, such a problem is called the TSP or the travelling salesman problem, where the feasible solution is a tour or a circuit, which means a solution 1, 2, 3, 4, 5, 1 is feasible. A solution 1, 4, 5, 2, 3, 1 is feasible for a 5-city problem. Now, can we define another kind of a TSP where I say that I want to start from 1. So, 1 is a starting node. Let us say my ending node is 3, but I want to go from 1 to 3 going through every other vertex once and only once. For example, 1, 5, 4, 2, 3 is a feasible solution to this problem, because I start with 1, I end with 3, I can go through this. I may have 1, 4, 2, 5, 3 is also another feasible solution. Now such a problem is called a travelling salesman path problem. It is called a travelling salesman path problem, where you want to find out a path from given I to j, such that in this path you go through every other vertex once and only once. You know the starting node, you know the ending node. Now these are feasible solutions to the travelling salesman path problem. Now there are times this travelling salesman path problem is also an important problem. There are quite a bit of work that has been done on the travelling salesman path problem. Now if we try to plot this, if you go back and draw a graph associated with this, let us say 1, 5, 4, 2, 3. Now this is a path. Now one important observation is that any feasible solution to the path problem is a spanning tree. By itself is a spanning tree. Now let us look at the length of this. Now this is 1 to 5 is 7, 4 to 5 is 6, 2 to 4 is 5 and 2 to 3 is 10. So this is 7 plus 6, 13 plus 5, 18 plus 10, 28. We also know for the same problem LMST is 26, which we have computed earlier. Therefore LMST is always less than or equal to L naught of the path problem. Now this is a feasible solution. So if we call, for example, L naught P as the L naught for the path problem, then L naught for the path problem is less than or equal to 28, but L naught of the path problem being a spanning tree, LMST has to be less than or equal to L naught of this. So LMST is not only a lower bound to the travelling salesman problem, it is also a lower bound to the travelling salesman path problem. Now if we draw our MST with 26, we would get 2, 4, 5, 4 to 5 is 2 to 5 is 6 and 4 to 3 is 8 and 1 to 5 was 7. So we got 5 here, 3 to 4 was 8, 1 to 5 was 7, 2 to 5 was 6, 7 plus 6 13 plus 5 18 plus 8 26. Now this is the LMST. Now if we want to, now in this path problem we wanted to do with 1 and 3. So straight away we have LMST is a feasible solution to this path problem, and therefore for this instance LMST is the optimal solution. So you could get the solution to this problem with the MST itself satisfying it and giving us a solution with L equal to 26. Whereas if we looked at a path problem not between 1 and 3, suppose we say the starting node is 3 and the ending node is 5. Suppose we do that, then your starting node is 3 and ending node is 5. Let us say a feasible solution is 3, 1, 4, 2, 5 with L equal to 3 to 1 is 8, 1 to 4 is 9, 17, 2 to 4 is 5, 22 and 2 to 5 is 6, 28 with L equal to 28 is a feasible solution to this problem. Now this LMST is again a lower bound to this with L equal to 26 is a lower bound to this. So we can actually say that the lower bound is 26, and then if we look at this, now if we draw this 3, 1, 4, 2, 5, this is a spanning tree. Now this is a feasible solution. So this should have a property that the degree of this is equal to 1, degree equal to 1, degree equal to 2, degree equal to 2, degree equal to 2. Now, L naught P will satisfy the property that the starting and ending nodes will have degree equal to 1, while the rest of the nodes will have degree equal to 2. Whereas, if we go to the MST, we have degree equal to 1 here, degree equal to 1, degree equal to 2, degree equal to 2 and degree equal to 2. Now, we know that for 5 and 3 the degree has to be equal to 1, while for the rest of the things the degree has to be equal to 2. So, here there is a violation. So, we could say that either this is in the solution or this is in the solution. So, we could do a branch and bound algorithm from here saying either D25 equal to 1 or x25 is equal to 1 or x25 equal to 0. Like this we can build a branch and bound algorithm to solve, to get the optimal solution to the travelling salesman path problem also. Right now in this lecture we are not going to elaborate on this, but the purpose is to show that it is possible to have a branch and bound algorithm to get the optimal solution to this problem, which uses the minimum spanning tree, because for this problem L naught should have some properties, and the minimum spanning tree, if it violates that, then it is always possible to get a spanning tree which satisfies that. So, this branch and bound algorithm at every node will solve a minimum spanning tree problem and tries to see whether this property of degree equal to 1 for 3 and 5 and degree equal to 2 for the others is satisfied. So, it is possible to do a branch and bound to solve the travelling salesman path problem also, but the more important understanding is that the minimum spanning tree is a lower bound to the path problem as well. So, with this we kind of come to the end of our discussion on the travelling salesman circuit problem and the path problem, and in the next lecture we will look at the Chinese postman problem.